Hi, my name is Mikhail Jaffer, and this is my 2020 Comenius Project. This year, I chose to independently research and develop my own unmanned aerial vehicle. However, this is no ordinary UAV. It's fully autonomous. It uses a system called S.L.A.M, which is similar to what Tesla uses in its autopilot. However, I had to develop my own algorithms and technology for it to be compressed and optimized for such a small device. The technology allows it to avoid a bunch of obstacles, along with map out its own environment.
Before we get into more detail about this machine, we need to discuss its importance and why I believe it will better this world. Thousands of lives are lost yearly due to events such as forest fires and burning buildings. Along with that, there are many inaccessible and remote areas where humans can't deliver or drop off items like medical kits, water, and food to ones who need it. Many of these problems can be reduced by the use of UAVs. However, the most useful UAVs excel in three areas: speed, range, and battery life. Commercially manufactured UAVs that excel in these areas are too expensive and break easily. So my solution was to build a UAV that excelled in those three areas while also being cost effective. My design parameters consisted of using a customized racing UAV so that'd be quick, a receiver and transmitter that allowed the UAV to fly up to 3 kilometers away without losing any clear connection, and also a battery that gave the UAV a flight time of around 19 or more minutes. Along with that, I also wanted the UAV to be completely autonomous. So what I did was I utilized a system called S.L.A.M, which stands for Simultaneous Localization and Mapping. And essentially what this enables me to do is utilize a series of components such as cameras and sonar sensors and allow it to work together with algorithms I programmed. And the algorithms will stitch together the data from those cameras and sonar sensors to create a 360-degree view of the world for the UAV. And this will allow the UAV to not only avoid obstacles at any direction or at any angle in its path, but it will also get rid of the need for GPS, which is a very expensive component, because it will be able to map out its own environment and pinpoint itself within that environment.
Some design improvements I made while building this UAV was trying to make a modular FPV system. An FPV, or first-person view system, is something that allows you to see the drone's onboard camera in real time from something like a tablet or phone. What I wanted to do is make this modular so that while the drone's grounded, in seconds the user can switch out the camera for another type of camera or some other device. And so I achieved this in some sense. What I was able to do is make it so that within a 60-second period, the user can switch out the regular FPV system for an infrared camera. And so the use of this would be when the drone is searching through something like a building that's on fire, it can detect heat prints or heat signatures of people or objects that would be in the building that might alarm or be of some sort of use to the people, emergency personnel going into the building.
To see the materials I used or my building procedure for this UAV, you can scan this QR code up here, which will take you to a website that gives a more in-depth review of the whole project. And along with that, here are some photos of the final product.
Now it was time to test the UAV. The way I did this was by manually flying it and comparing it in stats including speed, range, and battery life against commercially manufactured UAVs at the low end, average, and high end price ranges. I did these tests 5 times, and here are the average results.
As I mentioned earlier, one of the main goals I had with this UAV is to make it cost effective. Currently on the market, the only UAV with similar autonomous capabilities is a $1,000 cinematography quadcopter developed by 3 MIT grad students. However, this UAV utilizes readily available materials and only costs $350. I was able to cut a large portion of the costs out by using the S.L.A.M algorithms instead of the GPS. The practical applications and possibilities of this technology are endless. Some examples that come to my mind right away are how it can be used for autonomous air delivery on a commercial scale and even in emergency situations. Along with that, it can be used to survey hazardous buildings or areas before emergency personnel enters to reduce the amount of casualties that occur. Ways I intend on improving upon this technology include continuing to build the modular FPV system to give it access to a wider variety of cameras and sensors. Along with that, I want to make the whole drone entirely modular so that you could switch out parts right away, and also add on parts such as something that would allow it to carry a cargo load that would be of larger size, such as like medical kits or supply kits and things of that nature. Also, one main possibility that would revolutionize the uses of this technology would be creating a network of these UAVs so that they could fly in a synchronized swarm through the sky. And this comes back to the point of it being cost effective, so that instead of having to spend thousands upon thousands, if not $10,000s of dollars to utilize this technology to its maximum capabilities, you can spend a fraction of that price and still take advantage of the maximum potential it has to better this world.